Welcome, everyone. Thanks a lot for joining us today. Appreciate you coming out to reInvent in general, but also to see our session here. I know it's been a good week, hopefully, for everybody. Been to a lot of sessions, probably, and probably getting excited to go to the party tonight, so thank you. So today we're going to talk about AWS Wavelength. This was announced in Andy's keynote a couple days ago, and we're working towards launching Wavelength next year. It's available today in Select Pilot, and you'll hear a little bit about how that pilot's going from one of our customers today. That's the Softworks team. And if you want to take a look at Wavelength and get any notices about it as we start rolling out next year, please go to aws.amazon.com/wavelength, and there's a sign-up form there. So in addition to Wavelength, we're going to also talk about local zones. And so Wavelength and local zones both help bring AWS Cloud closer to the edge to help solve use cases that need more use cases that need low latency. With me today are Ishwar Palekar, who's a senior principal engineer at Amazon Web Services, focused on Wavelength and telecommunications companies, as well as James Altman, Director of Publishing Operations for Bethesda Softworks, and Robert Duffy, who's the CTO of id Software. Appreciate them coming. They'll tell you about how they're reducing latency and bandwidth to give developers a great gaming experience, and tell you about how they've been showing a hands-on demo of Doom running at the edge in the Verizon booth, although I think the expo hall is probably closing at this point, so might not be able to see that at this show. So those of you that are here, why should you care about low latency access to compute resources? Well, we all encounter examples of latency in our daily lives, everything from telephone lag or congested expressways, and even when there's lots of bandwidth, we know that the number of hops or the distance something travels matters. And so emerging classes of applications that we're talking with customers about need increasing amounts of compute and storage devices that are closer to those end users and devices. And device makers could try to add in the compute and storage necessary into the devices, but that would lead to a lot of extra cost and size and drains on battery life. And so they're looking for other options. And the 5G network holds the promise of a lot more bandwidth and a lot less network latency that these mobile devices can access. However, even with the networking advancements in 5G networks, today mobile devices still have to cross a lot of hops in order to get from that device to the cell tower, to the mobile network, to the internet, and then to wherever your compute's running, probably in the cloud. And so that application traffic, as it travels through all these extra hops, it adds a lot of latencies. In fact, these latencies can add up to hundreds or more milliseconds. And that's just too much for some of these emerging classes of applications. And our team thought a lot about what we should do in order to help customers solve these problems without forcing them to fix the mobile devices to try to do these use cases that might be really hard. Like imagine adding a GPU to your phone, for example. And we thought about it, and we decided that the ability to combine the low latency and high bandwidth of 5G networks with the AWS Cloud would be a great way to solve this problem. And that's what led to AWS Wavelength. So Wavelength brings AWS services to the edge of the 5G network, minimizing that latency, minimizing those hops that you have to go through to get to the compute that's running your application. So application traffic can go from those mobile devices directly to the application servers without ever leaving the mobile network. And this prevents the latency that you'd otherwise have and enables customers to take full advantage of the advancements of 5G. So customers then can deliver immersive experiences like game streaming or AR, VR. Devices like robots or cars can now make complex decisions that might require more computing power than they'd have traditionally inside their device. And so by bringing AWS compute and storage closer to end users and devices, we can unlock a lot of capabilities, probably things that we've never even thought of here today. I think of the analogy of when folks first started thinking about how mobile phones could have a lot more compute and storage, and what were the sort of applications that people imagined at that time. They probably never imagined the sorts of applications that we all have on our Android and iPhones today, right? I mean, half of these things are just all net new that people have just created, and I think that the same thing's going to happen with the advancements enabled by wavelength. So you deploy your applications to a wavelength zone. And the nice thing about a wavelength zone is it's just an AWS infrastructure deployment that's embedded in a telecommunications provider's facility. So it behaves just like an existing AWS availability zone. You create a subnet in it. You can start creating AWS resources like EC2 instances and EBS volumes in it. And it just provides that consistent developer experience that you're used to. And so that allows you to build those low latency applications that you want using familiar AWS services and design patterns. And you can deploy the portions of your application that need low latency into a wavelength zone while running other parts of your application back in the region. So you might want to store information in S3, or you may have a back-end web service that can still run in the region, and then you just deploy that in the region and deploy maybe front-end parts of your application in the wavelength zone. Another benefit for customers is that with wavelength, you get capacity close to your end users and data with all the standard AWS benefits you're used to. So everything like pay-as-you-go pricing, no commitments, and the ability to scale up and scale down on demand. So you don't need to worry about trying to purchase compute capacity or in various telecommunication providers' data centers or anything like that. You just basically use AWS as you're used to using AWS. And then the last benefit is that with AWS Wavelength, you are able to expanding AWS to deliver low latency all around the world. So we announced it in Andy's keynote that in addition to Verizon here in the US, we have partnerships with KDDI in Japan, SK Telecom in Korea, and Vodafone in Europe. And we'll be announcing more partnerships going forward as well. So now that you understand a little bit about the benefits of what we announced, let's talk into some example use cases. So every end user wants to have low latency access to applications, and we can see the impact of higher latencies on the customer experience. So for example, this is an example that Andrew Certain wrote about in a recent blog that shows how even hundreds of milliseconds of latency difference can impact abandonment rates. If you look at, even though there are fewer pages served at higher latencies that are shown in green, they're responsible for a disproportionate impact on the abandonment rate, which is shown in red. And emerging interactive applications like game streaming and virtual reality and real-time rendering require even lower latencies than what were showed inside that screenshot there. Sometimes even approaching single-digit or tens of milliseconds of latency to end users and devices. And so local zones and wavelength give you that ability to address those problems by deploying your application into more regions that are closer to the end users and devices. And luckily, we have the Bethesda team here to tell you a little bit about this use case firsthand. A second use case is edge data processing. So use cases like industrial automation and smart cities and IoT can generate vast amounts of data. And using wavelength makes it possible for these use cases to avoid some of the buffering on uplinks or downlinks or even the data transfer, which is particularly useful for large objects and streaming video data. Wavelength also saves storage and battery power on the device because the data doesn't need to stay or be processed on the device. For example, in-vehicle fleet management systems and data from mobile IoT devices are good candidates to be pushed directly to the edge for fast local processing and to reduce the quantity of data that's sent across the internet. And then a third use case is machine learning inference at the edge. So today's devices are constrained in CPU, memory, and power, but they still need to perform analytics in real time for solutions such as self-driving cars, predictive maintenance, and robotics. And these smart machines not only need to know what's along their path, but to be able to react to changes in that path in real time. So the traditional model of kind of slowly updating maps and location information kind of days or weeks after the fact or after changes is no longer going to be sufficient for these sorts of use cases. And so we're working with partners like Mapbox to process lots of sensor data in real time and doing that at the edge to make better maps. Imagine changes happening to a road in real time, being able to be responsive to other users of that mapping software right then and there. And relying on the cloud reduces the requirements on the devices. So that makes it easier to train and update models. You don't need to make complex deployments to the devices. Instead, you're just managing your analytics models directly in the cloud, just as you always do today through AWS regions and availability zones. Only now you have access to wavelength zones and local zones. And then another example is robots that may not even have internet connectivity, but they may have mobile network connectivity, can use cloud-based prediction to determine things like location and avoid collisions by sending video up to the 5G edge. Or they can augment basic local models by processing exceptions at the edge. So managing these models on wavelength simplifies the connectivity and the data collection and analysis from a large number of sources. Okay, so I've oriented you a little bit to some of the problems that application developers have and the services that we've announced to address some of these problems. Let's dive a bit deeper into how we're delivering these capabilities. Over to Ishwar to tell you a little bit more about the details of 5G on the edge cloud. Thanks.
Hello, my name is Ishwar Parulkar. I'm a senior principal engineer in AWS Compute Services and the lead architect behind Wavelength. I'm going to give a quick overview of 5G and then dive a little deeper into what we at AWS mean by the 5G network edge, what wavelength zones are about, how they're built, and how developers can use them to build applications. So we've had a new generation of mobile networks approximately every decade, starting with the first generation, which was just analog circuits, communication circuits for voice, followed by the second generation, which just was a transformation to digital technology. The third generation was about adding bandwidth for data, supporting data. And the fourth generation was just another notch of more throughput and data to support broadband and video. We are at the cusp of the fifth generation now. And 5G is going to be very different than what 4G and 3G were compared to the previous generation. It's not just about high throughput, high bandwidth, but it's about a lot more. It's about addressing the use cases that Chris talked about earlier. And for that, 5G will address three dimensions. It's not only about high capacity, as I mentioned earlier, but it's also about ultra-low latency and massive connectivity, the ability to connect a very large number of devices to the network. So at one end, you have ultra-high definition video, which requires high bandwidth. You have applications such as AR, VR, gaming, which require low latency. And then there are applications such as smart sensor networks, which have a very large scale of connected devices. And the 5G network is expected to address all of these variety of use cases with the same physical resources. So these are very different characteristics of networks, but they need to be deployed from the same physical resources. So there's the concept of network slicing, of creating virtual slices across the network, which, using the same physical resources, addresses these different cases. And the International Mobile Telecommunications Body has put quantitative targets, as you can see on this slide, which are orders of magnitude higher. And the 5G networks are being developed or designed to meet these targets. But how do you achieve these targets, which are orders of magnitude higher and have multiple dimensions? So there are various sets of technologies that are being deployed. And I'm just going to give you a little flavor of the type of technologies that are going into building these 5G networks. So first is a set of wireless technologies. In that, one of the things that is happening with 5G networks is the usage of higher spectrum, or the millimeter wave spectrum, because with a higher frequency spectrum, you have wider bands, frequency bands that you can use, which result in higher bandwidth. Secondly, there's antenna technology, which is being used to increase throughput, called massive MIMO, or multiple input, multiple output antennas, where you have a single antenna with small sectors dedicated or targeting individual mobile devices, giving higher throughput. Then there's the idea of building a different topology with smaller cell towers. So today, a cell tower typically covers a radius of about 1 kilometer or 2. With this topology, you would have smaller cells which would cover a radius of around a few hundred kilometers. So this way, you can pack more towers in the same geography, reutilizing the same frequency spectrum over a wider range of devices. So these are some of the technologies. There's more, but there's this one category of technologies which is in this space, which help achieve some of these objectives of 5G. The second set of technologies are around virtualizing network components. So today, most of the network components like radio, cellular radio, the mobile packet core, are done using dedicated appliances. So these are dedicated hardware appliances with integrated software in them. With 5G, and they started a little before 5G actually, these components are getting virtualized. So you have virtual appliances or software appliances in the form of virtual machines and containers being deployed on general purpose servers. Additionally, the software appliances or the network components are being split into control path and data path. And what this gives is a tremendous amount of flexibility in deploying network components across the network. That brings us to the third part, which is kind of what's relevant here in terms of wavelength and the 5G network edge, is that now, given the flexibility of being able to virtualize components, the flexibility of splitting control and data, you can start placing these components at different parts of the network, and you get a lot of flexibility in having termination of the mobile network closer to the edge so that you can reduce latency. Additionally, to network components, you can also run applications in the network edge. So this is a brief overview of the kind of technologies that are going into building 5G networks. Now, looking at the edge of the 5G network, let's see what we mean by edge computing. There's different notions of edge. The 5G network edge is a very specific notion of the edge, and I want to get a little deeper into showing what we mean by 5G network edge. So here's end-to-end network. You have mobile cell towers connected to the CSP network, or a communication service provider, or a telecommunication provider network. This is a proprietary network owned and managed by the CSPs, which goes to a transit peering point, which in turn connects to the public internet and routes you to AWS regions. Now, as you can see, that the amount of hops, network hops, or network distance that traffic has to cover to reach an application in the region is significantly large. So it's resulting in round-trip latencies of the order of 100 milliseconds. You have to go through the public internet where it's best effort routing, so there's no tight control over the routing, which results in higher latencies, as well as the number of network hops that come into play here. Now, if we were to run compute inside the CSP network, within the CSP network, a few things happen. Firstly, your network distance goes down. Clearly, you're traversing fewer number of hops, but also you have tightly controlled QoS and routing on these parts of the network, which result in latencies of the order of 10 milliseconds going down to single-digit millisecond, depending upon where in the network your site is. And for the same reasons, the tightly controlled QoS, very tightly controlled routing, the latency jitter is also reduced between different mobile devices across different access points. So it's predictable latency, reduced latency jitter, which is very critical in applications that require synchronization between the end devices. Thirdly, for applications that upload a lot of data and need a lot of processing of that data, if done within the CSP network, saves a lot of backhaul bandwidth. So take, for example, machine learning for object recognition of 24/7 video streams being streamed up for surveillance. So you have a large amount of data being uploaded for processing, for doing inference and learning for recognizing objects in these video streams. So if we were to do this inference of these video streams within the CSP network, you would save a lot of data going back to the region. So that's a large part of the network, a large part of the data that you don't need to send through that part of the network, resulting in a lot of savings. So as you can see, it's by being inside the CSP network that you get some of the benefits. And that's what we mean by AWS at the 5G network edge or wavelength. We are embedding racks and servers within the CSP network in partnership with Verizon in the US and others globally, Vodafone, SK Telecom, and KDDI. So let me dive a little deeper into how we build these wavelength zones and how you can use them. So here's the same network again. And so essentially, a wavelength zone is a physical site within the CSP network where we are putting in AWS infrastructure and running AWS services on top. That's basically what we mean by a wavelength zone. Just digging a little deeper, I wanted to point out a few key characteristics of wavelength zones. Firstly, as I mentioned, it's AWS designed infrastructure, same as in the region. So we have designed racks, with power distribution systems, with cabling, with top-of-the-rack switches for integrating into the network. But these hold servers that we use in the regions today, the same servers. So essentially what you're getting is a piece of the AWS region infrastructure in a wavelength zone. Secondly, most important characteristic is the fact that they are hosted in a site within the CSP network. So if you look at a CSP network, it comprises of cell towers, various traffic aggregation points. There are aggregation points at metro aggregation level. There are aggregation points at the regional level. And there are physical sites there which can host IT equipment. And what we're doing in partnership with our telco partners is using these sites to deploy the AWS infrastructure in there. And now, depending on the site, the size of the site, the capacity that's available in these locations vary, but it's essentially hundreds of these sites going up to thousands in the future. Third characteristics of wavelength zone is the fact that it's managed and monitored from the AWS region. So wavelength zones are tethered to the regions with a link that's used to manage and monitor the infrastructure. The control plane that runs the AWS services and EC2 instances and some of the other services also runs in the region. So this is another key defining characteristic of a wavelength zone, which is the fact that we have region connectivity for managing and monitoring. Lastly, it's integrated within the CSP network. And this is, again, very key to the latency piece that we discussed. You have mobile devices through the CSP 5G access network directly accessing instances in a wavelength zone. So they don't have to go over the public network. They don't go out of the CSP network, but directly from the mobile towers through the CSP network, through tight routing, they directly can be attached to instances in a wavelength zone. So this deep integration, this tight integration is another key factor in getting the latency and the promise of the 5G bandwidth to developers. So 4 defining characteristics of what wavelength zones are. Now let's see why we think we are different compared to what the industry has been attempting to do. So there are various efforts in the industry to build what are called MECs, or MEC or MECs, standing for multi-access edge computing. But we believe the way we built wavelength zones is much more powerful for developers for the following reasons. Firstly, it's a single pane of management across regions and wavelength zones. So as I mentioned earlier, the control plane for the wavelength zones runs in the region. We have a link that tethers wavelength zones to the regions. So the control plane runs in the region. We manage and monitor them from the region. So you have a single console, a single pane of glass to run applications in the region as well as in wavelength zones. Right? So I think that's very powerful. Secondly, you have the same operational consistency. Again, for the same reason, the fact that we are tethered to the region and we run control plane in the region, any patches, any upgrades, any new versions of software is immediately reflected in a wavelength zone. So there is no inconsistency between what you're getting in a wavelength zone versus what's available in the region. Thirdly, the pace of innovation is also the same. So we at AWS innovate very rapidly. We are constantly delivering new services, building new features and capabilities in our regions. And all of those will be immediately available in wavelength zones because, again, of the connectivity to the region. Lastly, there is flexibility in deploying applications in the region versus wavelength zones. The same application can run in a region or a wavelength zone, and developers have the flexibility to choose depending upon characteristics of the particular applications or cost and other factors. And this is very useful in scenarios such as failover, where we need to move some of the applications or workloads from the edge to the region. So again, it's a seamless extension of the region to deploy applications. You can deploy applications in the wavelength zone or in the region, and you can move them around, and the experience is the same. So again, 4 characteristics that make our approach to delivering edge computing in 5G networks unique compared to some of the other approaches that are being attempted in the industry in this space. Now, how do we plan to deploy this? Let's look at the US. We have 4 regions here. We pick a market where we see demand, and we'll deploy a wavelength zone in partnership with Verizon, as we announced a couple of days ago in Andy's keynote. And based on how we see demand grow, we will be creating many more wavelength zones across the country. Note that these are not actual sites. This is an illustrative slide that shows the scale of what is possible very rapidly. Now, we will be deploying every wavelength zone looks the same in terms of the physical infrastructure. The physical sites are there. So it will be a very rapid expansion to multiple wavelength zones very quickly. And because of the partnership we have with other CSPs in Europe and Japan and Korea and others to come, we see this global footprint expanding very rapidly. Now, how would developers use wavelength zones? So firstly, each wavelength zone is connected to a region, as I mentioned, to run the control plane, to manage and monitor. But this is under the hood. Developers do not have to worry about that. But the same link is used for another purpose, which is to extend the VPC from a wavelength zone to a region. So developers can create a VPC in the region, create subnets and launch instances in the region, but they can extend that VPC to wavelength zone, where you can again launch subnets and run instances. So components of your application that are latency sensitive could run in the wavelength zone, and the ones that are not as latency sensitive can run in the region, but in the same VPC. And the VPC can expand or extend across wavelength zones as well. So you could have multiple wavelength zones in different parts of the country or the world, and you would have the same VPC extended across them. And then we have a construct of what we call the carrier gateway to enable developers to connect to endpoints that are outside of the VPC. So these could be other region endpoints. This could be the access network as shown here, the CSP 5G access network, or it could be other endpoints as well. But the carrier gateway will enable developers to connect their applications and instances to the access network and devices. It will allow developers to connect to other services and endpoints in the regions that are outside of the VPC. Some applications might require third-party or other servers which are in some other data center or internet, not in part of the region. And the carrier gateway will also allow developers to access those endpoints. So as you can see, there's a lot of flexibility between running components of your application in the region, in the wavelength zone, in servers which are outside of the regions, outside of VPC wavelength zones, and connect to various access networks directly. So here I've shown 5G access network, but there could be other networks that could be available, just such as fixed line and other access networks, where you could use the carrier gateway to select which network you would want to connect to. So now let's look at a specific example. I'm taking a typical gaming application as an example to show how you would use wavelength zones and the different options that I mentioned to build an applications. So a typical gaming application has a gaming server or gaming engine, which has latency-sensitive tasks such as rendering or encoding. Then there are typically services like a player state service that stores or that keeps track of statistics and sessions of players so that when you pause and restart, you can retrieve the session state. And then there's data around runtimes and other statistics that's stored in S3 buckets, or you could have game images that are in S3 buckets that need to be downloaded. So a developer would first choose the market or the geographical area they want to serve end users in with low latency. Like I showed the Chicago metropolitan area in the slide with the US map. So maybe that's the area that the developer wants to address, or it could be a selection of multiple zones, multiple wavelength zones. The developer would create a VPC in that chosen wavelength zone and the region that it's connected to, or it could be across multiple wavelength zones that the developer chooses. You'd launch instances in the wavelength zones for running the components of the application that are latency sensitive, like the game server. And you would deploy components of the application that are non-latency sensitive in the region in the same VPC. And using the VPC in the region is the same as today. You could have components that are outside of the VPC connected as VPC endpoints, or you could have components within the VPC as well. And the gaming image typically would be stored in S3 buckets, and it would be downloaded through the carrier gateway so that the application, those application components can run on instances in the wavelength zone. The other key piece we have in wavelength is a service discovery mechanism that enables mobile devices to connect to the right endpoints or the right applications across wavelength zones. So the service discovery has a registry in which all the instances that the developer creates across wavelength zones are registered, along with an understanding of the topology of the wavelength zones and the latencies to the different endpoints. So when a mobile device wants to use the gaming application or wants to run the game, it will query the service discovery, which will return the right appropriate wavelength zone and the instance to connect to for achieving the latency that's desired. And then the CSP network will route that device through the 5G access network via the carrier gateway to the right instance. So as you can see, there's a lot of flexibility in terms of using the different capabilities of wavelength zones and the connectivity with the region and the access mechanisms for the different endpoints that we have provided through the carrier gateway. So this was one example. Obviously, you can create a variety of applications. We are very excited to put this capability of AWS Wavelength in the hands of developers, and we're looking forward to seeing what interesting use cases developers come up with, given this powerful capability. Now over to James and Robert to talk more about how they are using wavelength zones to run games from the cloud.
Thank you very much. Thank you guys for coming out, and thank you again to Amazon for having us out as partners. So we're here to talk about cloud gaming. And more specifically, we're here to talk about the technology that we've built for cloud gaming, streaming games from the cloud to a local device, and how that works with wavelength zones and 5G to have the best streaming experience possible. So I work at Bethesda. I'm the director of publishing, and at Bethesda, we are always trying to create new, innovative, fun experiences for our players. But it's important to remember that games are not just an entertainment medium. Under the hood, they are really complex pieces of software. And so we need to be innovative in that software and pushing the boundaries of our technology to provide great experiences for our fans. And this is something that id Software knows and understands really well. This studio has an incredible legacy. It is the studio that created Doom and Quake and Wolfenstein. It is the studio that invented the first-person shooter and modern virtual reality. And the beauty of an id game like Doom is that it blends amazing, innovative game engine technology with fun, fast-paced gameplay, which is why those games feel so great when you play them. And so it's that legacy of innovation and expertise in game engine design that led to Orion. This is our new streaming technology that will help power the future of games. And the future is on the cloud. So if you think about what cloud gaming means, it's important. It's helpful to think about how we got here. People to get games used to have to go to the arcade. You used to have a hardware that was custom built to run a single experience. And eventually we shifted to have games in the home. People can have PCs, consoles, and that made games much more accessible to millions of people. But think of all the friction you have, even today. You have to have the expensive upfront purchase of the PC or the console, the eventual obsolescence of that hardware. You have to replace it. You got download times, you got patches, and you're basically confined to your couch. It's not easy for you to take your games with you wherever you go. But with the cloud, with cloud gaming, that all changes. You can play the highest quality games on devices you already own, like smartphones and televisions and tablets and low-powered laptops. And you're using the horsepower of those cloud servers to provide incredible experiences. And the type of experience that was once only possible on expensive home hardware. But it's also important to realize that to give that kind of experience, there are limitations inherent in the technology. The instance you're playing on is not just a couple of feet away. It is, in some cases, tens or even hundreds of miles away. So that's something we have to deal with and mitigate to the maximum extent possible so that you're having that fun, fluid, fast-paced experience that you're used to. So when we're thinking about these issues, you can think about, streaming a game is not like streaming a movie on Netflix. We can't take as much time as we want to compress. We can't buffer. All of that data that you're pushing around is expensive for service providers, and it can be expensive for consumers if you have data caps. And not to mention home networking environments can be spotty. You can have signal interference, and you can have multiple devices all sucking up the available bandwidth. So we have to mitigate that. Gaming also requires a ton of compute power. It's not easy to deploy that kind of GPU power, which is a good reason we're working with Amazon on this. And then, of course, there's latency. Latency is the killer. If you have latency, game over. Hashtag literally unplayable, not worth continuing. But let's shift to now talk about the Orion solution specifically, how we're mitigating latency and bandwidth and compute, and how that works with wavelength technology and 5G to deliver that incredible experience. So on the hardware side, the server spins up a game instance. and the game engine that powers that experience begins to deliver data. And it does that by rendering frames. So that frame will get passed through a hardware encoder where it is encoded and compressed into a digital video image that is sent over the internet to a client device. And that device can be a smartphone, it can be a TV, laptop, where it's decoded into video that you can see, you can interact with, send your signals back to the server, and that whole process starts all over again. Now, this has to happen 60 times a second. So if there's any latency there, you're going to feel it. Now, the traditional approach to mitigating some of these problems has been with hardware. And what you see is people trying to build and design custom video encoders to make the process faster, or design new video encoding algorithms. But all of those approaches fail in their fundamental premise, and that is the belief that where you optimize for a game stream starts at the hardware encoder level. And that just isn't true. We thought that we could achieve significant savings if we started at the game engine level, and that's what we did. Orion is game engine technology, and it optimizes the game itself for performance on the cloud. It reduces bandwidth, it reduces latency, and it reduces compute. So you can see how when you combine that with wavelength and 5G, other technologies that reduce bandwidth and latency, you're going to achieve an incredible experience. So we used Doom as our test case. We did that because it represents the most difficult problem for a streaming service to solve. Doom is a fast-paced, first-person shooter, so you cannot hide any latency in third-person animations. It runs at 60 frames a second. It is in native 4K resolution. And basically, our belief was, the hypothesis, is that if you can stream Doom, you can stream anything. So my colleague, Robert Duffy, CTO of id Software, will tell you a little bit about how we're using the game engine to have that incredible experience.
Yeah, so I'm going to talk about a couple of techniques that we use in Orion. We have a number of other techniques as well, but these are two of the main ones. The first one's called we call GGME, Game Generated Motion Estimation. And if you're familiar with video encoding, the most expensive part that happens is frame-by-frame comparison for motion, because the motion is what drives the compression and ultimately results in the size of the video and how good a quality you're getting. Most modern AAA shooters already generate pixel-perfect motion vectors every frame. And so what we do is we basically take the game-generated motion data and we inject it into the video encoding process and skip the most expensive part. And what we end up with is better bandwidth because the compression's better because the motion estimation's perfect. And we're able to, have a higher quality video at effectively a lower bandwidth because of this particular technique. Another technique that we use is we call DPP, deferred pixel processing. And, again, modern AAA games, modern engines do a lot of post-processing from lens cracks in lenses, lens flares, film grain, also the UI elements that are on the HUD are typically done post-processing. And what we do for DPP is we defer some of that work to the client if the client supports it. And in many cases, because if you think about film grain as the base example, the one thing you don't want for encoding a video is entropy in the image. You want the same image every frame. And so every single frame, we're just slapping on, here's all this noise into the image, which just destroys it. And DPP in particular can save dramatic amounts of bandwidth. The Doom 2016 with the post-processing turned on, which is how we ship it, DPP will reduce typically 20 to 40% of the overall bandwidth. So that takes your stream needs down from 25 megabits to maybe 15. And again, if you're playing in a contested house with kids and and significant others, that 10 meg might make the difference between having fun or not. So.
And here's what that looks like. So this video is showing us toggling Orion on and off. With Orion turned on, those techniques turned on, what you see is clear picture. It's coming in at low latency, typically saving about 20% of latency per frame. Then you turn it off, and you have video corruption, you have lag. Basically, it's terrible. So when Orion gets toggled back on, you'll see bandwidth will go down again, latency will improve, compute will improve. See, it clears right up just like that. So again, you can see how there's some complementary technologies when we're talking about wavelength and 5G. Streaming a high-quality console or custom PC level experience presents unique challenges, and we built Orion to address those problems based on decades of experience of game engine design, trying to squeeze every ounce of latency just out of the equation. But layering on Amazon Wavelength and 5G makes that experience so much better. And it also delivers on the promise of being able to play anytime, anywhere. Today's mobile networks, for example, could never stream a game like Doom. But we're up and running right now. We are delivering an ultra-low latency AAA experience on Verizon 5G mobile devices via Wavelength.
And delivering the experience, being able to deliver the kind of experience we want to deliver is where partnering with AWS and Verizon made a lot of sense. We've had Orion running on top of AWS for quite a while, but again, we heard about the opportunity to work with them on this pilot program, and overall it's been fantastic. It's all a bunch of brand new technology. The 5G's new, Wavelength's new, Orion's relatively new, so it couldn't have gone better from a customer perspective to work with them. They've been great, one of the things that we've noticed, and I think one of the things that we're excited about is we're going to be able to, as we have more compute at the edge, we're also going to be able to start designing game experiences that were just never possible. That you can't do this on a PC, no matter how nice it is or how expensive it is. And that's, I'm very excited about the potential for that for us as developers and for consumers. The other thing about the 5G that we found out was we sent a couple of guys from our quality assurance team to Chicago to live test the pilot program, not too long ago. And their experience was basically that 5G is better than Wi-Fi. So, and you think about a year or two down the road, whenever you have 5G coverage at your home, you may not even need Wi-Fi. So overall, our experience has been fantastic.
Yeah, and we're going to be able to power some really incredible gaming experiences in the future with this technology and with our partnership with AWS and Verizon. So thank you guys very much. Come by the Verizon booth if you can catch it before we're out of there. Really appreciate it. We're going to be up in the corner here for some Q&A if you guys are interested. And otherwise, we would really appreciate it if you filled out a survey. Thank you guys very much. Thank you guys for coming out.